This video begins Unit 8. And as you might remember from last week, I told you that Unit 8 is going to be on stoichiometry. So you can see the spelling and the definition on your screen. And I've also provided the pronunciation for you. So it's just stoichiometry. Stoichiometry. So what is it? Well, the definition, as you can see on your screen, is the relationship between quantities of reactants and products in a balanced chemical equation. So you might remember from last week that anything to the left of your arrow, here's your arrow right here, that just means yields or goes to. Everything to the left of that arrow, so in this case nitrogen and hydrogen, well, those are your reactants. And anything that's to the right of your arrow, well, those are your products. And in this case, we only have one product. It's NH3, which is ammonia. And last week, you guys were putting numbers in front of each substance in the reaction in order to follow the law of conservation of mass. We know that matter is not created nor destroyed in a reaction, only rearranged. And so you were adding those numbers out front in order to balance the equation, making sure that we had the same number of each element on both sides. So in this case, you can see there's a 1 out in front of nitrogen. We have a 3 in front of our hydrogen, and then a 2 in front of NH3. And so by putting those numbers out in front, that makes sure that we have 2 nitrogens on both the left hand and the right hand side, 6 hydrogens on both the left and right hand side of that arrow. So what are these numbers that we were putting out in front of each compound or element? Well, they were more than just coefficients. It's actually representing the number of moles involved in the reaction. And so that leads us to molar ratios. So each one of those numbers, well, it's telling us something significant. What are molar ratios? Well, in that balanced chemical equation, you have 1 mole of nitrogen, 1 mole of N2. And for every mole of N2, you have 3 moles of H2 that will react. And for every 1 mole of N2 and 3 moles of H2 that reacts, well, you're going to produce 2 moles of NH3. These are our molar ratios. Okay. Now, from your molar ratios, you can get conversion factors. And so if I have 1 mole for every 1 mole of N2, I have 3 moles of H2 that will react. Right? So you just write them as a fraction. For example, I could also say for every 3 moles of H2 that react, I will produce how much ammonia or how much NH3? Well, it would be 2 moles of NH3. Okay. And as is typical with any conversion factor, you can flip-flop these as well. You could say, well, for every 2 moles of NH3 that are produced, I would need 1 mole of N2. Okay, so these are just some examples, all right? Our molar ratios, well, this is our molar ratios. And then I'm writing them as conversion factors down here, or fractions. These are our conversion factors, okay? So what is the best way to understand this process and fully understand stoichiometry? Examples. Examples are your best friend. So we are sticking with the same example that we've been using. So we've got nitrogen and hydrogen are our reactants, and that goes to ammonia, which is NH3. So we have a question here. How many moles of H2 are needed to produce 25.8 moles of NH3? So we have a few things going on here. Well, it's asking for how many moles of H2. So this is what I want to solve for here, moles of H2. And well, what was I given, or where do I start? So 25.8 moles of NH3. Well, that was my given information. And this is where I'm going to start. Okay, so we're going back to dimensional analysis. All right, so I'm going to start with 25.8 moles of NH3. And I'm going to use my dimensional analysis chart, that grid that we've used before. And just as previously, well, if I have moles of NH3 in the numerator, well, in the denominator next to that, I need the same unit, because remember, dimensional analysis allows us to get rid of units we don't want. So I need to have the same unit in that denominator. So I'm going to have moles of NH3. Well, since I'm dealing with moles and I have a balanced chemical reaction that involves moles, the number that's going to go out front is going to be the same number that's represented by NH3. So I've used colors to help kind of guide you guys here. So we have 2 moles of NH3. And again, that came right up here from this balanced chemical equation. Well, that's great. That allows my moles of NH3 to cancel, but what am I solving for? What molar ratio do I need to use here? Well, I wanted to solve for moles of H2. So moles of H2 are going to go up top. Well, and what number is going to go in front? Well, from my balanced chemical equation, I have a 3. So it's going to be 3 moles of H2. Okay, so this gives me, this is my conversion factor, or my molar ratio here. For every 3 moles of H2 that react, I produce 2 moles of NH3. That is what I've put on in my grid. So now that those moles of NH3 cancel, I would be left with moles of NH2, or I'm sorry, moles of H2. And that's exactly what I wanted to solve for. So I know my grid is done. Everything is set up. All I need to do is put into my calculator the math, right? So it's 25.8 times 3. And then you're going to divide that by 2, because remember, as you go left to right across the grid, you multiply, and then you always divide the top by the bottom. So what do you end up getting when you do that math? You get 38.7 moles of H2. Okay. Let's go on to another example. This one is a different balanced chemical equation. You probably guys remember this from last week. You've seen this a few times. So I've got phosphorus and oxygen on the left-hand side, and then diphosphorus pentaoxide on the right side. And my question is, how many moles of P2O5 are formed from 3.45 moles of O2? So again, my given information, well, they gave me 3.45 moles of O2. So this is going to be where I start. And what do I want to solve for? Well, I want moles of P2O5. So that's what I'm going to be solving for. So I start always with my given information, 3.45 moles of O2. Put that in my grid. Since I have moles of O2 in the denominator, I need moles of O2 I have moles of O2 in the numerator, so I need moles of O2 in the denominator. So how many moles of O2? Well, again, you look back up at this balanced chemical equation up here. You see O2, well, you have 5 moles of O2. And for every 5 moles of O2 that react, well, how many moles of P2O5 react, right? That's what I'm solving for. I want moles of P2O5. So up here, it's going to be moles of P2O5. And in this case, when you look at your balanced chemical equation, it's 2 moles of P2O5. So again, you do the math. Because my moles of O2 are going to cancel, I have moles of P2O5 left over. That's what I wanted. So in my calculator, 3.45 times 2 divided by 5. And in this case, I'm going to get 1.38 moles of P2O5 are produced. Okay. Sticking with that same problem, I have another question. How many moles of P, or phosphorus, are needed to react with 32.1 moles of O2? So again, I have my given information here. This is where I'm going to start. I am solving for moles of P, so this is what I want over here. And so I start off with my given information, 32.1 moles of O2. Put this in my grid. I have moles of O2 in the numerator, so I need moles of O2 in the denominator. Well, how many moles of O2? Again, it's going to be 5 moles of O2, which I get, again, up here from my balanced chemical equation. Well, what do I want to solve for? I want moles of P, moles of phosphorus. So that's going to go up top. Well, how many moles of phosphorus? Again, I look up here at my balanced chemical equation, and that's going to be 4 moles of phosphorus. So my moles of O2 cancel. I'm left with moles of P, which is what I wanted to solve for. So I know my setup is done. I do my math in my calculator. It's 32.1 times 4. And then you're going to divide that by 5. And that's going to give you 25.68 moles of phosphorus. Okay. Again, examples are our best friend. So now I'm going to move on to another equation, or chemical balanced reaction. Now this one has 2 reactants, 2 products. Okay. Don't let that intimidate you. The process is still the same. Okay. You just have a little bit of extra information. And if you want, I highly suggest maybe even you pause the video here, work it out on your paper, and see how you do before you watch me work through the problem. All right, so the question is, if 5 moles of copper chloride react with aluminum, how many moles of aluminum chloride are produced? So same process. This one's a little bit more wordy, but the process is the same. Okay, you were given 5 moles of copper chloride, copper 2 chloride, and you want to solve and figure out how many moles of aluminum chloride are produced. So notice it says produced, right? So produced, well, that's going to be on the product side, right? And it is right here, aluminum chloride. So this is what we want to solve for. We want moles of aluminum chloride, okay? So as always, start with our given information. This is where we start, right here. 5 moles of copper 2 chloride in my grid. I have moles of copper 2 chloride in the numerator, so in the denominator you will have the same thing, moles of copper 2 chloride. Well, how many moles of copper 2 chloride? If you look at your balanced chemical equation, you have 3 moles of copper 2 chloride. And what do I want to solve for? What is my molar ratio or my conversion factor? Well, again, you look up here and you wanted moles of aluminum chloride. I'm sorry, I shouldn't have put that in blue. Moles of aluminum chloride. Well, that's in green, right? So that's right here. So 2 moles of aluminum chloride go up here in the numerator. Again, the whole purpose of setting this up is to cancel out units we don't want to get to the units that we do want. And what we're left with are moles of aluminum chloride. So you do the math again. It's going to be in your calculator if you want to use one. 5 times 2 divided by 3. So 10 divided by 3 is going to give us 3.33 moles of aluminum chloride. Okay. And last example, same problem, same reaction as before, aluminum with copper chloride. This time it's asking if 7.5 moles of aluminum chloride are produced, how many moles of copper chloride were used? Okay, so again, keywords produced, so that aluminum chloride is, of course, going to be on the product side. And then that was my given information, so that's where I'm going to start. And what do I want to solve for? Well, I want moles of copper chloride. This is what I want, right? It's saying how many were used, so that was on the reactant side, okay? And you can see both of those whenever you look at the balanced chemical equation. So I start 7.5 moles of aluminum chloride. I'm going to set up my grid. I have moles of aluminum chloride in the numerator. I need moles of aluminum chloride in the denominator. How many moles of aluminum chloride? Well, you look at the balanced chemical equation right over here. 2 moles of aluminum chloride. What do I want to solve for? Well, I want copper 2 chloride, and that is right here. So 3 moles of copper 2 chloride. Moles of aluminum chloride cancel. You're left with moles of copper 2 chloride. I forgot the 2. So in your calculator, 7.5 times 3 divided by 2 is going to give you 11.25 moles of copper 2 chloride. Okay. So that was the last example I have for you. Now that you've watched this video, you might want to watch it again and kind of review your notes. But in Schoology, you have 8.1, check your understanding. Okay. It's going to include questions about doing stoichiometry problems. And there's also going to be some information about lab equipment and including a lab sheet for you to look at. So go ahead and you can work on check your understanding in Schoology. If you have any questions, don't forget I have office hours today from 2 o'clock to 2:30.